Hi guys, bear with me on this. I haven't done one of these videos in quite a while, so I'm learning again how to put all of this together. I'm going to try to teach you Unit 14 this way. Unit 14 involves understanding what a spontaneous reaction is all about and using two thermodynamic functions, both entropy and Gibbs free energy, to determine the spontaneity of a reaction. In part 1, I will define spontaneity, and then I will also define entropy and explain how that can affect the spontaneity of a reaction. So a spontaneous process is one that will occur without outside intervention. It means that the reaction is product favored. It basically means that anything that takes place without you adjusting or affecting variables is considered spontaneous. So if you were to put a piece of ice on the table and it was above 0 degrees Celsius, the ice would melt without you having to help it out. It is the same idea when we add sodium chloride into water or when iron rusts. We don't necessarily have to do anything to get that reaction to occur. It will happen on its own over time. Some non-examples would be if we were trying to boil water, but the temperature was only 75 degrees Celsius at 1 atmosphere of pressure. Of course, we know water boils at 100 degrees Celsius. So in order for us to get water to boil at 75 degrees Celsius, we would have to adjust the pressure. So this would be an example of a non-spontaneous process. Also, water would not be able to freeze at 15 degrees Celsius. So a reaction is spontaneous in one direction, but non-spontaneous in the opposite direction. As seen in the example below, liquid water converts to solid water at negative 10 degrees Celsius. We know this is true because water will freeze at 0 degrees Celsius. If you take a look at the non-spontaneous reaction, you will also see that this is a true statement. At temperatures above 0 degrees Celsius, say at 10 degrees Celsius, the liquid water would not convert into solid water automatically. Spontaneity tells us nothing about the speed of the reaction, only about whether the reaction will occur in the forward direction without any outside intervention. We've discussed reversible reactions in our equilibrium unit, so you are aware that a reversible process is one that can go back and forth between states along the same path. The path taken back to the original state is exactly the reverse of the forward process, and there is no net change in the system or the surroundings when the cycle is complete. Water freezing and melting is an example of a reversible reaction. It is also an example of a reaction that is spontaneous in the forward direction, but non-spontaneous in the reverse direction. The early idea for why certain processes were considered spontaneous was exothermicity, meaning that if a process released energy into the surroundings, it lowered its potential energy state. We came to find out that there were other reactions that were considered endothermic that were also spontaneous. So they had to determine what the other factor was in determining spontaneity. And the current conclusion is that the driving force for all spontaneous reactions is an increase in entropy. So the best scenario of a spontaneous reaction is one in which the reaction will lower its energy, thus it will have a negative delta H, or be considered an exothermic reaction, and a reaction that moves to increase its entropy. This is important. Basically what I'm saying is any reaction that has a negative delta H and a positive delta S will always be spontaneous no matter what temperature. So what is entropy? Entropy is a measure of the disorder or randomness of a system. It is the natural tendency to go from order to disorder in our universe, thus from a lower to a higher entropy. Just like enthalpy, it is a state function. It doesn't matter the pathway that the reaction takes to get from the start to the stop. The second law of thermodynamics says that the entropy of the universe increases in a spontaneous process. Entropy can be defined in terms of probability. It can also be described by the extent of randomness for a system. Substances will take the arrangement that is most likely, which is most random. As you can see in the picture, on the left, we have a gas that is completely closed off to the other side of the vessel. And when we open up that vessel so that the gas can move to the other side, you now can see that there are more opportunities for those molecules to position themselves in that space. So they have become more random because of the larger volume that we have given them. There are several ways for you to determine the entropy of the system. The first would be to look at the physical states of matter, solids, liquids, and gases. When you have more ways for the molecules to be arranged, you will have a greater disorder or a higher entropy. So solids that are closely packed together, as seen in the picture, have very little disorder, and they are considered very ordered. So we would say a solid has the lowest entropy. As the solid converts to a liquid and thus a gas, there will be more space between the particles, the forces of attractions become weaker, and the particles can organize themselves into a lot of different ways, and thus there will be more randomness in the substance. Gases have the most randomized positions. Solutions have more entropy than the actual solid solute. That is because when the solid solute gets dissolved into the solvent, there will be more possible arrangements for those dissolved pieces than if they were to stay together. More complex substances that are larger, will have more disorder because there is more vibrational and rotational motion than less complex substances. And if you have a complete gaseous system, so a reaction in which all gases are present, if the products have a smaller number of molecules or moles, then the entropy will decrease as well. So let's take a look at a few examples and predict whether the entropy will increase or decrease. So if I give you a deck of playing cards that are neatly tucked away in their box, that would be a very ordered box of cards. If Johnny decides to play a 52 card pickup and scatters them all over the family room, now we have increased the disorder of the cards and entropy has increased. If your parents ask you to clean up your room and it is spotless, we would say that it is very ordered, and then as days go by, that room becomes more disheveled because over time you start to move things around, and once again the disorder will increase. If I have a solid piece of ice changing into liquid water, the solid is very organized, and as the attractive forces are broken, the liquid particles can glide past one another. That's going to give you more randomness, more arrangements, and we would also see an increase in entropy there as well. However, if we see a gas changing into liquid water, we're going from a physical state where there was a lot of randomness into a state now where there are somewhat of an attractive force holding the particles together, and there's just some movement, but not a tremendous amount of movement like we saw in the gas. So entropy would decrease. If we take carbon dioxide gas and we dissolve it into Coke, a liquid, once again we are decreasing the disorder of the carbon dioxide gas. It's actually being compartmentalized into a smaller container, and it will have attractive forces then between itself and the water. In F, a chemical reaction between gas molecules that results in a net decrease in the overall number of gas molecules will also be a decrease in entropy. Less moles of gas would mean less randomness. And then the last one, which I don't think you can see on this slide, would be the volume of a container contains gas that is increased from 5 liters to 10 liters. As the volume increases, there's more space, so that gas can take up that more space, and it will have more possibilities and thus greater randomness. So there would be an increase in disorder. In this second example, gaseous CO2 would have the higher entropy. because there's going to be more randomness in movement of the gas particles versus solid particles. And in part B, the nitrogen gas at 0.001 atmospheres will have a larger volume than nitrogen gas at 1 atmosphere. Remember that pressure and volume are inversely proportional to one another as long as temperature and moles stay constant. So once again, an increase in volume due to the smaller pressure will give more randomness to that nitrogen gas. And in our last set of examples, this time we are actually predicting the sign of entropy. If entropy increases, the sign for delta S will be positive. If the entropy decreases, the sign for delta S would be negative. So for part A, solid sugar is added to water to form a solution. Solid sugar had a lot of order. As it moves into the water, it will have more randomness, so there will be an increase in entropy, so that is a positive delta S. For part B, iodine vapor condenses on a cold surface to form crystals. That means that it's going from gas to solid form, and that would lower its entropy. Thus, we would have a negative delta S. If we take a look at example C, the thermal decomposition of calcium carbonate, you can see that we're going from a solid, and then you are producing a solid and a gas. So in this example, we are increasing the entropy because some of the particles were able to now expand and have more randomness in gaseous state. And then the last one, which looks like to me is cut off for you as well, is the oxidation of sulfur dioxide. This reaction has 3 moles of gas on the reactant side and only 2 moles of gas on the product side. Because the number of moles is decreasing as we go from the reactants to the products, the entropy will decrease as well, and the delta S will be negative. The last thing we should mention is that the second law of thermodynamics basically tells us that the entropy of the universe is increasing. The entropy of the universe is actually a combination of the entropy of the system, which is the reaction, and the entropy of the surroundings. Now, the entropy of the surroundings is affected by enthalpy. We're not going to go into any details with how to calculate delta S universe. All you need to know at this point is that if delta S universe is positive, then the process is spontaneous. If delta S universe is negative, then the process is non-spontaneous, but it's spontaneous in the opposite direction. And if delta S universe is 0, the process is at equilibrium. Delta S universe is usually a difficult value to calculate, so in our next video, we will be looking at delta G, called Gibbs free energy, and that thermodynamic function will help us predict the spontaneity of a reaction with better accuracy. We will use the entropy of the system to help us determine Gibbs free energy, period. At this time, I'd like for you to make sure that you read through your notes, that you watch this video over again if you need to, and I would like for you to try the problem set 1 that is on Canvas. The answers have been given to you, and then I'm also asking that you work on the review packet and complete the sections up to entropy. Thank you. Have a good one, and I hope this wasn't too awful. Bye.